Yes. Okay, so I think we're ready to start. If anybody's outside, if they want to come and join. So welcome to this session on the second day. So it's a session on quantum security. We have two talks. One of the talks will be actually remote, but the first one, so it's a pleasure to welcome Andrea Schottenloher, and he's going to speak. His talk is going to be quantum linear key recovery attacks using the quantum Fourier transform.
Thank you. So I want to hear it. Okay. So as entitled, the purpose of this work is to do key recovery. So let's say you have block cipher on n bits. That's a permutation of n bit strings with varying fixed unknown key. This thing, we can always find the key k. We have access to that by trying all the possible keys. That's what we do classically in the exhaustive search. And an attack is when you have a procedure that finds the key, but faster than this. But today we're interested in the quantum setting. And the quantum setting, we know that we have a faster recursive search, which is given by Grover's algorithm. And it can work in times to the unit size of k, key over 2 instead of unit size of k. But that's just rows. And an attack in the quantum setting is simply a procedure that finds the key faster than Grover's search. In this talk, we're interested in linear cryptanalysis. And the motivation is the following. First of all, linear cryptanalysis is a very powerful technique to find key recovery. Second, advanced linear key recovery attacks use the fast Fourier transform, more specifically the fast Morrow-Hadamard transform, special case of that. And when you put together in a sentence Fourier transform and quantum algorithms, the thing that comes to mind is the quantum Fourier transform, which is known to be very efficient and underlies most of the exponential quantum speedups we have, including Schwartz algorithm. But the previous work on linear attacks in the quantum setting doesn't use the QFT, or at least doesn't use the QFT in key recovery mode. So what exists is a work by Capron et al. That was using Grover's algorithm, basically over-like speedups, to find key recovery attacks. And also very recently, and actually concurrently to this work, work by also Yamada, which uses the QFT, but speaks up only linear distinguishers, certain types of linear distinguishers. So in this work, we're interested in using the QFT, but to accelerate key recovery attacks. So this is going to be about quantum algorithms, but hopefully all the horrible technical details of quantum algorithms are in the paper and not in the talk. So the only thing we need to remember for this is that when we work with quantum algorithms, we work with quantum states, and these states are superpositions. So for example, n qubits will give you a superposition of all the possible n-bit strings with complex amplitudes. Now, the problem with these amplitudes is that they describe the state, but these are not values that you can exploit immediately. The only thing you can do with that is measure the states, and then if you measure the state, you obtain one of the possible values x with the probability that depends on the square amplitude. So you cannot like measure everything. You cannot know all the amplitudes of a quantum state if you have a state like this, and that's really quite a difference. But still, what we do is we perform computations which modify the amplitudes, and in the end, the state becomes something that is interesting to us. In particular, one of these computations is the quantum Fourier transform in the flesh. So, in particular, this is going to be actually the Morrow-Hadamard transform, which is a Fourier transform but binary. So, imagine that your quantum state contains the amplitudes, which are actually the values, the outputs of some function f from n-bit strings to -1, 1. There is a very simple operation, it's actually pretty basic, that transforms this state into a state in which the amplitudes are now encoding the Morrow-Hadamard transform of the function f, which is defined by this formula. This is really important because, of course, classically, computing a Walsh-Hadamard transform costs you much more time. But again, the difference is in the quantum setting, you're computing this on the amplitudes, but the amplitudes are not values that you actually know at this moment. Also, the thing we need is quantum search. Quantum search generalized compared to Grover's algorithm. Imagine that you have an algorithm that produces a quantum state, and in this quantum state, there is someone that you're looking for, and it is flagged. Well, it's basically a qubit here, which is either 0 and 1, and it's 1 for the element you're looking for. Now, it is possible to find such an element with a procedure that is basically going to repeat this setup multiple times and iterate over that. And basically, the number of calls you need to make is 1 over the amplitude of the good element. This is why in robust algorithm, you have to do the size of k over 2 iterates to find the right key k when you're looking for it. This is basically it. Okay, so this was actually the introduction. So now we're going to enter linear cryptanalysis, and after that, we're going to move on to the quantum physics. So linear cryptanalysis. It is very efficient, as I said. It works as follows: by exploiting linear approximations of a given cipher or given function. And the linear approximation is simply the choice of an input mask, an n-bin string alpha, an output mask, also an n-bin string beta, such that the function alpha dot x dot product plus, this is actually absorbed in that case, but beta dot e of x is biased. And the quality of this approximation, basically the bias that you can expect, is related to a quantity that we call the expected linear potential. It's basically the correlation average over all possible keys. I'm not going to enter all these details. So we have this ELT quantity, which determines if the approximation is good. And of course, if it's large enough, because there is this approximation that exists for E and not in general, you have a distinguisher, a linear distinguisher that you can use afterwards in a key recovery attack. So now I'm going to explain how the key recovery attack works. A very simple example. This is actually from Matsui's work in the 90s. Imagine that you have part of a cipher here that is approximated with this approximation alpha beta, and you append some last rounds to this, and this is your whole cipher, EK. And the last rounds depends on some guess of some key bits, little k, and you won't find that. And imagine also, to simplify that, you know everything, you have the whole codebook, and you can make, you can create the entire codebook for the cipher. Now, the idea is you're going to guess the bits that appear here. And if you guess them right, by decrypting the last round, you're going to observe this EM, the actual one. And it has an approximation. So we're going to see this approximation. If you guess them wrong, then you're observing a random permutation. It doesn't have any approximation, and you won't have the same statistic. And this statistic of interest is what we call the experimental correlation, like this. And it's basically going to be bigger if the approximation alpha beta appears. So the idea is, well, basically you take all the possible input outputs x and ek of x, you compute the experimental correlation for all possible guesses of the last round subkey. And when it's bigger, you have a good correlation. You just find which one of them has the highest or one of the highest experimental correlations. And there are some statistics which are well detailed in the previous work. So the right subkey is basically around, as a correlation, is around square root of the ELP, and the wrong subkey is going to be around the minus n over 2. It can be also positive or negative, but we take that in absolute value. That's the basic last one back. But there's still no FFT yet, right? And I promised you the FFTs, so here it comes. Imagine now that the last one is actually very simple. It's only one. And after that, you have a key addition, like always in those ciphers. And the key here is going to be of n bits because everything is simple this way. And so this is your cipher. The idea of the FFT from Collar et al. In 28 is that it is going to allow you to compute the experimental correlations faster. So recall that you have this formula, and which depends on the last round, and then the guess of the sub key Z here. You're going to rewrite this as, in order to introduce two functions, f and g. F is going to depend on the cipher. So this is the part where you have the ek minus 1 here. And g is going to depend on just the last one. And the formula for the experimental correlation becomes actually the discrete convolution of two functions, function f and g. And so computing the correlation for all possible guesses of C is actually computing the discrete convolution of f and g, untitled. And we have something very, very powerful, very interesting, and very nice that relates the convolution to the Fourier transform, always in that case, the Walsh-Hadamard transform. Because computing the convolution of f and g is simply computing the dot product of the Walsh-Hadamard transforms and then doing the transform operator. And also with some like, yeah, some coefficients that I'm certainly want. So the algorithm is simple. Just compute the Walsh-Hadamard transform of f. You compute the Walsh-Hadamard transform of g. You do a pointwise product. You compute the Walsh-Hadamard transform again, and you have all the correlations. And the fast Walsh-Hadamard transform algorithm does this in time n times 2 to the n. So now the total time to compute all the correlations is only n times 2 to the n. Instead of, well, the previous one, the naive one, was going to be 2 to the 2n. That's much faster. So that was for the linear cryptanalysis using the FFT. And now we're going to see how we can try to do that in the quantum setting. And in the quantum setting, I'm going to introduce what we call a correlation state, which is simply a quantum state with the correlations, not intensive at all. And the question, well, the most technical point is going to be how we compute it. And then another interesting point is going to be, well, how we can use that to do some cryptanalysis. But first, computing this stuff. And the idea is to do it in the same way that we did it classically. So recall that you have the two functions f and g, and f which depends on ek, and g which was the last round here with the linear masses alpha eta. And the correlation is the convolution of f and g. So I'm going to show you how you compute the convolution of the functions inside the amplitudes of the quantum state. First of all, because the convolution is just a dot product, but under a Hadamard transform, and as I said, the Hadamard transform is trivial, we just have to compute this thing with the product of the two functions in the quantum state. And this is going to be very oversimplified presentation of that. Here is the algorithm. First of all, you can't compute f, the function f, in the amplitude. Doesn't seem easy because f is defined with the say for ek, and also putting something in the amplitude is not always easy, but actually it's just you have to flip the phase, multiply it by -1, depending on the value of alpha dot ek -1, and actually that's it. Okay. Second step, of course, is to apply the Walsh-Hadamard transform, and you can obtain the transform coefficients of f in the amplitude. That's pretty standard thing. And a problematic step, or at least a complicated one, is that you have now to compute the Walsh-Hadamard transform of G, but to compute it for real, like with an actual algorithm, an actual circuit to do it. And what I say by digital is that it has to appear here in the quantum state. It's like having to compute it classically, same problem. Fortunately, G only depends on the last one. And actually, this is going to be a rather simple function in actual applications. We're still not trained. And now another technical step is that now this is here in my quantum state, but it's in the wrong place. I don't want G in my quantum state here. I want it in the amplitudes of my quantum state. So I have to somehow transfer this value into the amplitude. And it's actually possible. It involves what we call quantum state preparation, aka rejection sampling techniques. And it also involves a small amplification layer that I'm purposefully missing, not putting in these slides. And after doing all of this, you obtain what we wanted. So with the product of the two functions, and after that, the convolution of the two functions in the input. So we have, let's say, a black box, and that creates this quantum state containing the correlations in the input. And the time complexity of this contains queries to the cipher and computations of the Fourier transform of G, which is the worst. Okay, but how is this useful? It's actually not also not easy to exploit, but there are two limits. In the classical case, we compute all the correlations and we find the highest one. Well, that's pretty easy. Once we're able to compute the correlations, exploiting them is okay. And here in this quantum setting, we can create a quantum state which encodes the correlations in the amplitudes. And I said at the beginning of this presentation, that's useless. Having the amplitudes here having the correlations here is not that great. It would be great if we had them with the Z here, but we don't. They're only like analog values. You can think of them as like probabilities of measuring Z if you measure the state, but I mean, it's not like you can have access to. But still, you can use the fact that in this superposition of guesses of a subkey, the good one has a higher amplitude. Because of course, it's supposed to have a higher correlation, because there is a linear approximation that we're exploiting. So here is the idea of how to exploit this would be to use this state as what I call shortcuts in a quantum exhaustive search. So for comparison, imagine that the full key of the cipher is the subkey K plus some other part of the K prime. In global search, what you do is you start from a superposition of all the possible guesses of the key, and then you flag the right one just by checking the right one by encrypting through the plaintext and known plaintext hypertext. And after that, when you have something that you can amplify, you're going to repeat this 2 to the sine of K plus sine of K prime over 2 times to find the flagged right key. Here is what we do for comparison. In that case, we're starting with this correlation state, which is also a superposition of subkey guesses for the key K. And now what we can do is first of all, we can complete the key by adding a guess for K prime. So this guess for K prime is going to be uniformly superposed. And after that, we can still flag the couple K prime because it's a full key of cipher. We do the same thing as before. We test a few plaintext and hypertext pairs, and you say, this one is a and we obtain a superposition which is different from the previous one. And actually, in this superposition, the amplitude that is on the right key is slightly bigger. That's because, there is this linear approximation that exists. So we get an amplitude which is, we get a number of iterates, which is 1 over square root ELP times 2 to the K prime over 2. This is going to be smaller than previously. So hopefully we have actually a speedup against a global search like this. The only trouble with this, which is well unsolved at the moment, is that classical cryptanalysis purposefully uses very small values of the ELP. That's because you only need to distinguish. So you have a linear approximation, you stretch it as much as possible, and it's going to end up with a very, very small ELPs, a very, very small correlation, as long as you can still observe a tiny difference with the average case. And well, here, my quantum speedup depends directly on the ELP. Well, that means I get a very, very tiny quantum speedup. And the second problem is, of course, that building the correlation state here wasn't easy. But I just put all the details away. But in practice, it will require you to have quantum RAM, or sometimes also, if you prefer, superposition phrases. Still, I wanted to end this presentation just by taking a concrete example. Unfortunately, this is not a cycle that exists, or I mean, I just put it together myself. I don't know of any example that looks like this exactly. Imagine that you have a block cipher which is cut like this. So this is an ideal part. This is an ideal permutation, and it's an ideal cipher as well. And you have a key. You have n bits of k here and 2 n bits of k here. So the idea is to make something that is difficult to attack, classically, and easier to attack. Now, classically, to attack this, you basically need to get k prime, and then you attack the event so it takes you time to the 2.5 n. In a quantum setting, you can use the algorithm I just presented, and you will find an attack which is going to use time to the n times some polynomial factor. The attack is simply going to, well, still guess the key k prime here by using reverse search, and then solve the problem here, attack the remaining construction, but using the fact that there is a linear approximation somewhere. Well, basically, you use the last one's attack, so this is the last one, and the linear approximation is here, but it's, I mean, it's SAS correlation one because it's here. That would be the quantum attack. Well, it has a speed up, which is to the n against the 2.5 n, so it's better than Grover search. But we really know how to do that with Simon's algorithm. You combine the Grover search and Simon's algorithm. You use Simon's algorithm basically to attack the middle cipher, and it's already like a 2 to the n. The difference that I want to emphasize is that if you touch something in this construction, you can't use Simon's algorithm anymore. Everything breaks. For example, if I don't give you the whole playbook, you can't use Simon's algorithm anymore. If I put here a very tiny function like something that is almost linear, but not exactly linear, so Simon's algorithm breaks, and trouble like this. And in that case, the attack that I presented is going to remain, contrary to the Simon-based attack. In particular, it's going to remain if you only have the playbook and I can kill the other phrase. Okay, so now I'm getting to the conclusion of this. The idea of this work was using the QFT somehow to accelerate the statistical attack. Because usually what the QFT does in quantum algorithms is accelerating structural attacks like period finding, etc. The trouble is, well, it's still difficult to make it work. I do have 2 working applications so far, which basically the applications where classical linear cryptanalysis is great, orthogonal with the applications where this kind of attack in the quantum setting would be great. Everything will be solved if there was a very good quantum algorithm to find the largest correlation in the correlation state, but I'm not sure if it's actually doable if it's produced as a black box. Well, I leave the problem to you. And the report you can pay to Niprints and this.
Okay, thank you, Andrea. We do have time, about 2 minutes for questions. And if you have a question, please walk to the front. Question. So in your last slide, you're saying if to produce the state is in a black box, it seems so. What would be the alternative? What the state if it's not?
Well, if it's not, you have to do what I presented, which is not really satisfying. What I would like, so if it's produced in black box, prime seems very difficult, but it's not produced in the black box because we produces it. So perhaps somehow you can open up the black box again and I don't know, try to do something that allows you to solve this problem. But I don't know.
Okay, and so just a last question, can you see application for the same ideas for encoding amplitude, some statistical information related to key gas? Because in symmetric key, this is quite common that you have the last round, and have you tried anything?
Yeah. Well, I mean, applications of encoding things in amplitudes are certainly already everywhere in quantum computing. The application to binary cryptanalysis seems natural in retrospect because of these statistics that you compute to the FFT. My guess is everywhere when there is a statistic that involves the FFT, it's going to be, I mean, could be useful in this, but I don't have any other great examples in mind.
Okay, so if no further questions, so thanks, Andrea, for the interesting talk. So we have another talk now, but it will be delivered online. So if you just bear with me.
Can you hear me?
Yes.
Hello?
Yes, we can hear you.
Oh, okay.
So just 1 second. You just the slides.
Yeah, he's gonna be.
Okay. Okay, so we have a second talk of the session. The talk is titled Quantum CCA Secured Key Encapsulation Mechanism with Explicit Rejection in the Quantum Random Model, and it's going to be given by Jiang Xiang and his member. Please, you may go ahead.
Okay. Good morning, everyone. My name is Jiang Xiage, and I'm going to present your work on titled QC Secure Key Encapsulation Mechanism with Explicit Rejection in the Quantum Random Oracle Model. This is a joint work with Tianshu Shang and Ruixue. So let's get started. Here is an overview of this talk. I will first talk about the background and the motivation of our work. Then I will introduce our main results and the outline of the technicals. Finally, I will give a summary. Now let me talk about the background. In 2016, as a countermeasure for the threat of quantum computer, NIST studied the post-quantum cryptography standardization. They call for submission of quantum-resistant cryptographic algorithms for public key encryption, key encapsulation mechanism, and data signatures. In our work, we mainly consider the quantum security of CAM. So we next talk about the CAM construction in the NIST PQC standardization. In the CAM submissions to NIST PQC standardization, the CAM variants of Fujisaki model transformation are frequently used. It consists of 2 parts, the FO-like transformations and the modular FO transformations. These transformations are designed by Hoffman et al. And are used to transform a one-way CP secure or in CP secure PKE scheme into an in CC secure CAM scheme in the random oracle model. In more detail, the FO-like transformations act on the randomized PKE scheme. The modular FO transformations act on the deterministic PKE schemes. Here, the transformation with superscript bots is called the explicit rejection type. And its decapsulation algorithm outputs bots for an invalid ciphertext. The transformation with superscript cancel bot is called the implicit rejection type. And its decapsulation algorithm outputs a pseudo-random value for an invalid ciphertext. As for the subscribe M, the encapsulation algorithm of the transformation with subscribe M outputs GM star as the key. Will the encapsulation algorithm of the transformation without subscribed M outputs GM star C star instead. Here C star is the encryption of the plaintext M star, and G is a hash function. So in the random oracle model, a hash function is idealized as a random function that all parties have access to. However, in the quantum setting, a quantum computer can compute the hash function H on an arbitrary superposition of inputs. So to model that, the random oracle model should be lifted to the quantum random oracle model, and Theorem for short. In this model, the quantum adversary has quantum access to the random oracle. Okay, so in the Theorem, the in-CC game of CAM scheme is defined as follows. Here, the challenger sends public key PK, challenger cybertext C star, and the key KB star to the adversary. KB is either generated by the encapsulation algorithm or randomly chosen from the key space. The adversary has a classical access to the decapsulation oracle and quantum access to the random oracle. It finally produces a guess B prime for B. After obtaining the B prime, the challenger will output this value, which is 1 if B prime equals B. Otherwise, this value is 0. Beyond the Theorem, Bonnet and Zhang have considered a stronger quantum adversary that can perform quantum queries to the secret oracle. They introduced a new secret notion named indistinguishability under quantum chosen cybertext attacks, and QCC for short. In the Theorem, different with the in-CC game of CAM, the adversary of the in-QCC game of CAM can both make quantum queries to the decapsulation oracle and the random oracle. So in the Theorem, it's obvious that the in-QC security implies the in-CC security. Because the classical query to the decapsulation oracle can also be viewed as a quantum query, as long as we measure the query registers before and after the query. So now let me talk about our motivation. In fact, by the analysis of Appendix A given by Hoffman et al., we find the following relation between the FO-like transformations, which is that security of FOM bots implies security of all the remaining FO-like transformations. This means that the quantum security analysis of FO-like transformations can be simplified. We can only focus on FOM bots and prove its quantum security. The remaining FO-like transformations are also quantum secure. However, in the Theorem, the existing security deduction of FOM bots as given by Dan and Holmans is less tight than the state-of-the-art security deduction of FO-like transformations given by Kuchta et al. For the transformation FO console bots. To be more concrete, in this table, Q is the number of queries to the Q is the number of the quantum queries to the random oracle. Epsilon is the security bound of the underlying PKE scheme. QD is the number of the classical queries to the decapsulation oracle. This term is related to the corresponding requirement. Roughly speaking, the gamma spread property means that the cybertext generated by the underlying encryption algorithm have a sufficiently large entropy. The anti-injective property requires that the underlying encryption algorithm is the most injective function. The dirt here is the correctness error of the underlying PKE scheme, that is the probability of the decryption failure for the cybertext generated by the underlying encryption algorithm. And we also call a PK scheme is data correct if its correctness error is delta. Here we do not consider the data correct as a requirement because any PK scheme has a correctness error, only some are large but and some are small, and basic requirement of the PKE scheme is that it should have a negligible correctness error. So compared with the security bound of FOM console bot, the security bound of FOM bot still have a quadratic security loss and is less tight especially the term related to the corresponding requirement. Here, the secured bond proved by Holmans and Kuchta, they use the success probability of some correctness schemes to denote the correctness error. And we omit the term in this slide for simplify. So this raises a natural question. In the Theorem, can we give a secure reduction of FOM bond, or is the quadratic secured loose and has a tighter secured bond, tighter than this bond proved by Dan and Holmans? In addition, this relation also indicates that the security of FOM bonds implies security of FOM cancel bonds. However, it's not clear whether the opposite direction holds true. In other words, there exists another natural question. Does security of FOM cancel bond imply security of FOM bond? If the answer of this question is true, we can say that the security, the transformation FOM bond is as secure as its implicit rejection counterpart, FOM cancel bond. Okay, so now let me move on to present our results. For the first question, we gave an QCC secure reduction of FOM bonds and prove the following theorem. We prove that if the underlying PK scheme P is the correct and gamma spread, then in the Theorem, the inclusive security of FOM bonds can be reduced to the incipient security of P, or without a quadratic secured loose. And our secured bond is also tighter than those CC bonds proved by Dan and Holmans, even we accomplish a stronger in QCC security. For the second question, our answer is yes, but we need the requirements on the underlying PK scheme. In fact, we prove that if the underlying PK scheme is gamma spread, then in the Theorem, the inclusive security of FOM cancel bonds implies the inclusive security of FOM bonds. Okay, so this was the results. Now let me talk about our technicals in a high level. The core theorem of our work is the following theorem, theorem 2, which shows that if the underlying PK scheme P is the correct and gamma spread, then in the Theorem, the inclusive security of FOM bonds can be reduced to the incipient security of FOM bonds. We will give a proof outline of this theorem in this talk later. So first, let me talk about how we use this theorem to answer about two questions. For the first question, as given above, our answer is the following theorem. In fact, by using our core theorem, theorem 2, the proof of this theorem is very simple. First, by using our theorem 2, we obtain this inequality. Then by directly using the semi-classical 1-2 heading lemma proposed by Bani-Settle and the measure rewind measure 1-2 heading lemma proposed by Kuchta, we find the incipient security of FOM bond can be reduced to the incipient security of underlying PK scheme P. So combine these two formulas, we obtain this inequality. For the second question, we use our core theorem, theorem 2, to prove the following theorem, theorem 3, which shows that if the underlying PK scheme P is the correct and the gamma spread, then in the Theorem, the inclusive security of FOM cancel bonds implies the inclusive security of FOM bonds. The proof of this theorem is also very simple. First, by using our core theorem, theorem 2, for any adversary A against the inclusive security of FOM bonds, there exists an adversary A1 against the incipient security of FOM bonds satisfy this inequality. Then for adversary A1, there exists an adversary A2 against the incipient security of FOM cancel bonds satisfies this equation. The reason is that the only difference between the FOM bonds and FOM cancel bonds is a decapsulation oracle reserve. So if we only consider the incipient security, where the adversary cannot query the decapsulation oracle, the difference between FOM bot and FOM console bot can be ignored. So we have this equation. Then it's obvious that there exists adversary B against the in-Q3 security of FOM console bots satisfy this equation because the in-Q3 security must imply the incipient security. So finally, combining these two formulas, we obtain this inequality. Okay, I guess there is not enough time left, so I gave a simple proof outline of our core theorem 2. In the proof of our core theorem 2, we first simulate the quantum accessible decapsulation oracle (DECA) by using the extractable RO simulator proposed by Dietel. Then we gradually change the simulation of DECA by a sequence of games, game 1 to game 4. In the end, we find the last game, game 4, can be rewritten to an incipient game of FOM bots. So let's start with briefly introduce of the extractable RO simulator proposed by Dietel. Roughly speaking, the extractable RO simulator SF is a general version of the compressed standard oracle given by Zhangzhui. Based on a database register, SF has two interfaces, the RO interface ECO.RO and the extraction interface ACO.EF. The RO interface simulates a quantum random oracle edge by using the compressed standard oracle. The extraction interface is defined relative to a function f that maps oracle input output space into a space T. And the extraction interface can also be viewed as a unitary operation that maps basic state TDZ into state TDZ O plus X, where X is the smallest value that satisfies fx dx equals T. So the extraction interface is usually used to extract some information from the database state. Now we introduce game 1, which is identical with the QCC game of FOM bots, except that an extractable RO simulator SF1 is introduced, and the quantum random oracle edge is simulated by the RO interface ECO.RO. And the quantum accessible decapsulation oracle DECA is also simulated by using the extraction interface ECO.EF1. Here for simplify, we omit the detailed definition of function F1. And in our work, we prove that if the underlying PKE scheme is gamma spread, the difference between these two probabilities can be upper bounded by this term. In game 2, we design a new function F2 and replace the extractable RO simulator SF1 into SF2. The important property of the function F2 is that the implementation of the extraction interface ECO.EF2 only requires the public key PK. So the simulation of the decapsulation oracle in game 2 no longer requires the secret key SK. In our work, by using the compressed oracle Y2 heading lemma given by Chaikov's schedule, we bound the difference between these two probabilities by Q times the square of delta, where delta is the correctness error of the underlying PKE scheme. Actually, we use an adaptive version of the compressed oracle Y2 heading lemma, and the detailed proof of this adaptive version is given in our another work this year with the proof number 792. So in game 2, the quantum random oracle edge is simulated by the RO interface ECO.RO, that is to say simulated by the compressed standard oracle. So the computation of the challenge subtest C star needs to first query the compressed standard oracle by point M star. However, the instruction interface may disturb the simulation of the compressed standard oracle on point M star because it actually performs a computational basis test on the database register. But fortunately, we prove that if the underlying PK scheme is gamma spread, the disturb caused by the instruction interface ECO point EF2 can be upper bounded. We prove that we can transform game 2 to the following new game 3, with error terms QD times 2 to the.
You have 4 minutes just to. Sorry, June.
Oh, okay. Here always a new new independent random oracle with the same has the same input output space at edge, and in order to maintain the consistency, the simulation of random oracle catch in game 3 need to make a judgment that if x equals m star, the m star should be returned. Otherwise, the OR interface should be performed. However, the simulation of quantum random oracle catch needs the challenger plain text M star to make a judgment. But we prove that if the underlying PK scheme is the correct, the x with error term 2 delta, the x equals M star is equivalent to this value equals C star. So in game 4, we replace the x equals M star into this value equals C star. Now we can construct a new adversary without query the decapsulation oracle and only query the random oracle O and G as follows. It implements the extractable our simulator SF2 itself and simulates the quantum random and runs the adversary A in game 4. So it's obvious that B is the adversary against the incipient security of FOM bot. So we have this equation. Then we can directly change O to H since it's just a symbol, and this H is independent with this H. Okay, so I think it's time to make a summary. In our work, we give an inclusive security reduction of FOM bot in the Q-ROM, avoids the quadratic security loss and has a tighter security bound. We also prove that in the Q-ROM, if the underlying PK scheme is gamma spread, the inclusive security of FOM console bot implies the inclusive security of FOM bot. So we can say that so under the requirement of gamma spread, we can the transformation FOM bot is as secure as its implicit rejection counterpart FOM console bot. That is to say, security is independent of the whether the rejection type is explicit or implicit. Okay, this is the end of my talk. Thank you for your attention.
Okay, thank you. Let's thank the speaker. We do have time for a quick question. Okay, no questions. So I just have one big question. So your last statement, you say that there is essentially equivalence to the security for implicit and explicit. So does have any effect, for example, in this competition? I think I understand there's several schemes that have used the implicit rejection because of proofs that can work better. Do you think your results would have changed this decision?
I think it kind of changes it cannot change the decision because yeah, we prove that the security if one is secure, the another is also secure, but we need a requirement that the underlying PK scheme needed to be gamma spread. But for example, the winner, the cable, as far as we know, no one had computed the gamma spread this part number of the cable.
Okay. All right. So thank you, and thank everybody for attending. So there is some time now for a quick change of rooms. So we have a session starting in 5 minutes. Well, thanks, Jiangxia. Thanks, Jiangxia.
Thanks. Thank you.